As we dive further into forces, we're going to talk about uniform circular motion. And uniform circular motion, we are going to talk about tangential velocity and centripetal acceleration. It's not going to be a whole lot of rotation stuff. It's going to be more along the lines of things that are traveling in a straight line. So tangential velocity is the velocity of an object that is tangent to the circle in which it is traveling. And then we're going to talk about the centripetal acceleration, which means the acceleration will be center-seeking, or heading toward the center of the circle. So we have learned that velocity is constant for objects that are traveling in a straight line. In Newton's first law, the object will travel at a constant velocity unless an unbalanced force acts on it. I have a circle here, and this is as if we're going to keep an object in a circular path. The way we do that is by pushing toward the center or pulling toward the center. We're going to have some type of force acting toward the center of the circle. And the force that causes centripetal motion is going to always be towards the center. You can imagine twirling an object on a string. You're pulling that object toward the center of that circle at all times. So if we're going to have objects traveling at a constant velocity in a circular path, that object is accelerating even though the velocity is constant. And the reason the object is accelerating is because it's changing direction. And we calculate the centripetal acceleration, or the acceleration being center-seeking, because it's going to be in the direction of the force that we have here. Our force that is causing centripetal motion is going to be toward the center, so our acceleration is going to be in the same direction. And it's going to be v squared over r, where v is that tangential velocity. And you can look here that if we have velocity 1 and velocity 2, the velocity of the object is a constant magnitude, but it is changing direction. So in velocity 1 we're going to the right, velocity 2 we're going down, and the acceleration is perpendicular to that. And so we're talking about tangential velocity, velocity in a linear path but tangent to the circle. So let's attack an example. So we're going to have a mass of 4 kilograms, and it is going to be spun in a circle at a speed of 10 meters per second. And the tension in the string that is holding the object is going to be 5 newtons. We want to know what is the radius of that circle. So we know that the net force is going to equal mass times acceleration, but our acceleration here, since it's in a circle, it's going to be centripetal. And that's going to equal all the forces that are acting on the object, and we only have tension acting on the object at this point. We haven't talked about horizontal or vertical circles or the difference between the two, so right now we're just assuming it's an object in a circle with a tension acting on it, so that's the only force acting on it. And so we're going to have mass times velocity squared over r, substituting in v squared over r for our centripetal acceleration. And that is going to equal our tension. So mv squared over t equals r, reorganizing the equation to solve for the radius. So we're going to have 4 times 10 squared over 5. It's going to equal the radius, and the radius will be 80 meters. So that is a very simple case of how to solve for a variable using centripetal acceleration and recognizing that we have a net force that is the centripetal force. So now we're going to look at 2 examples, or 2 types of circles. We're going to talk about horizontal circles first, and then we'll go into vertical circles. Horizontal circles are nice because they don't have gravity. We're going to take gravity out of the equation. The object will still have weight, but it's not going to have like gravity causing it to change its motion. So we're going to have a car going around a track, and we're going to have a force toward the center. The object's going to have weight, and then it's also going to have normal force. So in this case, what we need to recognize is that our centripetal force is not a separate force. It's Not like friction is different than normal force. Those two are separate forces. What we have to recognize is that centripetal force is a net force. It's, what is causing us to head toward the center, to have a force to keep us in this circle. It could be multiple forces, it could be one force. In this case, with a car going around a horizontal track, the friction of between the object and the road is keeping the object in the circle, so that is our centripetal force. Friction is the centripetal force because weight and normal force cancel each other out. The net force is friction, and therefore that is the centripetal force. So centripetal force usually is a net force, and it's basically, and you can see by the equation that net force equals mass times the centripetal acceleration. So the net force is causing the centripetal acceleration, so our centripetal force is our net force. In this case, it's friction, not a separate force. All right, now on vertical circles. In vertical circles, we have to deal with gravity. And we're going to have our example here being a roller coaster on a circular track going vertically. And so I've drawn the roller coaster cart in 3 different spots, well, 4 different spots. And it's going to be traveling in I believe that's counterclockwise fashion. So I've drawn the tangential velocity at all those points. And then we have to draw our forces. So at the top, we're going to have weight down and normal force of the track pushing down as well. And then on the side, we're going to have normal force pushing us toward the center and our weight acting down. And at the bottom, we're going to have our weight acting down, but the normal force pushing up. The net force is changing at every point. So we're going to have to know at least these 3, and you can see that the one on the right, the object on the right, would be just like the object on the left, where the normal force is holding it toward the center. So 4 spots, but basically 3. And at the top, our net force is going to be mass times centripetal acceleration, and it's going to be equal to our weight plus our normal force. They're acting in the same direction. But at the bottom, it changes entirely, where our net force equals mass times centripetal acceleration is going to be normal force minus our weight. At that point, you can see that our net force, or our centripetal force, which is a net force, is going to be changing. One thing to remember at the top, when we're talking about an object barely hanging on, we're at the top of the circle, we're going through this on a roller coaster. If the roller coaster was not traveling fast enough, the cart would fall. But there's got to be a speed that we can travel at that we would call our minimum speed to be able to complete the circle, but the normal force of the track pushing back is 0, where we are barely hanging on, so much so that we are barely in contact with the track, and so much so that the normal force is negligible or 0. So if we were to try to find a minimum speed at that point, for us to be able to go around the track, the normal force would have to be set to 0. So when that happens, we have to recognize the only thing keeping us in a vertical circle at the top at minimum speed has to be the weight of the object. That way, the tension or normal force, or however we're staying in the circle, if we're twirling a ball in a circle on a string, or we're riding in a roller coaster cart, that the minimum speed, the normal force is 0, and the only thing holding us in the middle of the circle, or into the circle, is our weight. The next thing we're going to talk about are banked curves. And a banked curve is a lot like NASCAR, where you're going fast and you're not on a perfectly horizontal track, and so the track is actually at an angle. It's like an inclined plane. So we're going to have a mass on an inclined plane, and then we're going to represent the velocity so we can see it in 2 different directions. Well, now we're not going to do it like NASCAR. If in NASCAR you go fast and turn left, we're going to go fast and turn right, just for fun. And so if that's the direction of our velocity, that means that our picture on the left, that our velocity is going to be into the page. And how we represent that is usually by an X, saying it's going into the page. So we're going to have an X there, we're going into the page. The object is going to have weight, and it's going to have normal force perpendicular to the surface. We know that we're going in a circle, and so in order to be going in a circle, we must have a centripetal acceleration and a force toward the center holding us in there. So our acceleration at this point is to the right, and it depends on our velocity tangential to the circle and the radius of the circle. So go ahead and write those down, and we're going to the right here. So our forces, our normal force here, can be split into two different directions. By breaking up the normal force into two different components, we can find out which force is holding us toward the center. Our weight is perpendicular to our centripetal acceleration, so it is not our net force holding us in. And the normal force is at an angle. You can see that just by it being on the inclined plane. So we have to find what part of the normal force is holding us into the circle. So we're going to draw a bigger picture of the exact same thing up here, and we're going to break up normal force into two components. So if we draw a straight line from the top of the box here, we can see that that is 180 degrees. And that spot there is theta. The left side of the normal force is 90 degrees. On the right side of the normal force, it's 90 degrees. So if we say that's theta, the interior part of our triangle down there in the bottom left corner is 90 minus theta. So based on that, we can determine that that is theta at the top of our triangle there, right there next to the label Fn. So now let's look at our net forces, and in the y direction it needs to be 0 because we're not accelerating up or down here. So that is going to be our weight minus our normal force up, which is Fn cosine theta. And then our forces in the x direction is going to have our centripetal acceleration, and it's going to be Fn sine theta as the only thing that is acting toward the center and holding us in the circle. So for the y direction, we can move mg over, and mg is going to equal Fn cosine theta. And we can divide cosine theta and find the normal force. And then for the x direction, our acceleration is v squared over r, so we substitute that in. So mass times v squared over r is going to equal mg cosine theta, substituting that in for Fn, for normal force, times sine theta. And sine over cosine is something that we can change. We know that particular that it's tangent theta. I don't know exactly what I'm trying to say there, but anyway, masses cancel. It's v squared over r, and we have g tangent theta. So now we find our net force. Our net force in the y direction is 0, which is going to be mg minus Fn normal force cosine theta. And our net force in the x direction is going to be Fn sine theta, the only thing holding us toward the center of the circle. Solving for forces in the y direction, we have mg equals normal force times the cosine of theta, and we're trying to solve it for the normal force. So we would divide by cosine of theta, and our normal force would be mg divided by cosine theta. And then over here on the x direction, we're going to have mass. We're going to substitute v squared over r for our centripetal acceleration. And that is going to be equal to normal force times the sine of theta, and we're going to substitute what we found in the y direction for normal force in over here for the x direction. So we're going to have mg divided by the cosine of theta multiplied by sine theta, and sine theta divided by cosine theta is a trig identity that we know. Here the masses will cancel. We can rewrite it where v squared over r equals g tangent of theta. So that's where we're going to leave it for now. And before next class, I want you to figure out one thing, is what happens when we add friction to the scenario. Well, you know, we could slide up and down this ramp. So I need to know what happens when we add friction. So be sure to look that up in your book best you can, and we will practice a lot with this next class.